Hey, chemistry. I want to go through a limiting reactant problem. And you can see on the board that I have a couple things. First of all, we're going to use a dialectical journal. So with this, we're going to work on a problem, and you can see what the question is there. And on this side of your paper, you're going to show work. On this side of the paper, we're going to take a couple minutes and reflect on our work and see if we can't write out a sequence. The benefit of doing this is that the next time we go through this problem, if the context is a little different or the wording is a little bit confusing, what you end up with is basically a set of instructions to yourself as to how to process through it. And that can be really helpful to refer to, especially when the context changes. So we're going to do both of these things together and try to get a handle on how to do a limiting reactant problem. Now, what you're going to see on this problem is that there's a couple questions that are asked. First of all, one of the questions you're asked is about how much product you can make. But in this problem, we're given two different amounts of reactants, and we don't know which one runs out first. So really embedded in this question, there's two different things we have to find. We have to find out A, what's the limiting reactant, and then B, how much of the product can we make? If we go on, there's a second question here, which is how much of the excess reactant remains after the reaction is finished. And so there's really three different things that we're going to go through and be able to find. And we're going to write instructions for ourselves for these things as we work. All right, so let me go back to the beginning of this problem. Okay, so here we go. Take the reaction. We have ammonia reacting with oxygen to form nitrogen monoxide and water. In an experiment, 3.25 grams of ammonia are allowed to react with 3.50 grams of water. What mass of NO is formed? So notice I have underlined all the information that I might need, and I've circled what I'm trying to find. And that way, if you get lost as you're trying to go through this problem, or you get deep into the math and forget what you're trying to find, you already have it underlined and circled, and you don't have to reread the whole question. It just kind of keeps you organized. Okay, so we're trying to figure out how much of our product, nitrogen monoxide, we can form, but we don't know which of our reactants will run out first. Whichever reactant runs out first is going to stop the reaction, and it can't go any farther. It's going to limit the amount of product we can make. So we need to figure out what our limiting reactant is. Now, there's a couple different ways you can do this, but I'm going to show you one way today. So we're going to compare both of our reactants to our product. And whichever one forms less product limits the reaction and stops it with that much product made. Okay, so let's compare both of our reactants to our product. 3.25 grams of ammonia, and I'm going to convert that into grams of NO. Since that's what I'm trying to find anyway, I'm going to just go all the way to grams of NO. I might need a little bit more room, so let me put it here for now. Okay, so I'm in grams of ammonia. That's the unit I have. That's the unit I want to get out of, so I automatically put it on the bottom. Now, from grams of ammonia, I do have a relationship to moles of ammonia, but I don't have a relationship to anything else, so I have to go to moles of ammonia. That's not what I want, so I need another conversion factor. I want to convert out of moles of ammonia, and from there I have lots of different options. I can go to mass of ammonia, particles of ammonia, volume of ammonia, or moles of something else. Since my answer is in something else, I'm going to go to moles of something else. That something else being NO. And then I still need to convert moles of NO into grams of NO. Okay, so now I have my path laid out. Now I need to fill in those numbers. So the first number here, grams of ammonia to moles of ammonia, that's going to be molar mass of ammonia. So let's go find molar mass of ammonia. So I go look at my periodic table. I add up nitrogen plus 3 hydrogens. That's going to be 17.03 grams per 1 mole of ammonia. Moles of ammonia to moles of nitrogen monoxide, that relationship comes from the balanced chemical equation. So I do have a chemical equation up there, but it's not balanced. So I need to take a minute and balance it. 1 nitrogen, 1 nitrogen. I have 3 hydrogens and 2 hydrogens. So let's see. I'll give that a 3 and that a 2. Now I have 6 hydrogens, 6 hydrogens. I have 2 nitrogens. So let me put a 2 here. 2 nitrogens, 2 nitrogens. Now I have 5 oxygens on one side and then an O2 on the other. So I'm going to double everything. 4, 4, 6. So I still have 4 nitrogens, 4 nitrogens. Now I have 12 hydrogen, 12 hydrogen. And then I have 6 plus 4 oxygen. So this can be a 5. Now it's balanced. Okay, so the coefficient of ammonia is a 4. The coefficient of nitrogen monoxide is also a 4. Okay, and then I need molar mass of nitrogen monoxide. So I go to my periodic table, nitrogen plus oxygen, 30.01 grams per 1 mole of nitrogen monoxide. Okay, I have my equation set up. Now let's do the math. So 3.25 times 1 times 4 times 30.01 divided by 17.03. I also want to divide by 4, and I also want to divide by 1. And I get 5.73 grams of nitrogen oxide. Okay, so again, the key to these problems is knowing what your answer means. So if I use all of my ammonia, I can make 5.73 grams of nitrogen monoxide as long as I have enough oxygen. But I don't know if I have enough oxygen. So let's do this again for oxygen and see how much I can make with all this oxygen. 3.5 grams of oxygen. Again, I'm going to compare it to the same thing, grams of NO, so that I'm very consistent. So I want to get out of grams of O into moles of O, out of moles of O into moles of NO, out of moles of NO into grams of NO. Well, the molar mass of NO will be the same, so I can just fill that in. Now I have 4 NO to every 5 O2. Now I need the molar mass of O2, so I add up oxygen plus oxygen. That's 32.0 grams in 1 mole of oxygen. Okay, let's do this math and see how it comes out. 3.5 times 1 times 4 times 30.01 divided by 32, also divided by 5. also divided by 1. And I get 2.63 grams of NO. Okay, again, let's pause here and think about what our answer means. If I use all 3.5 grams of oxygen, I can make 2.63 grams of NO. So, which one is my theoretical yield of NO? Well, my oxygen is going to run out and stop the reaction before more NO can be made. So oxygen limits. I can make 2.63 grams of NO, and NH3 will be in excess. I'll have some of that left over. Okay, so this is our work. We have answered the question that was asked of us in A. Now let's pause and think through what we did. Okay, this would be a good time to pause the video and try to fill in these boxes that are on the right-hand side. First, what we do, then we decided to, next I decided to pause here and see if you can fill those out. All right, if I was trying to summarize kind of what I did here, I would say first, I calculated from one reactant, or I converted from one reactant to the product. Then I decided to do the same thing for the second reactant. I'm going to write this at the bottom. And then next, I looked at the amount of product I could make, and I found the smallest amount. So we're looking for the smallest amount of product. The smallest amount of product is what can actually be made. That's going to be your theoretical yield. The other one is not actually a theoretical yield. The other one can't actually be made because we run out of oxygen, right? So that one calculation shows us both what we can theoretically make in the product and what limits our reaction. Okay, so pause here. Another thing I want you to do is write yourself questions you have. Where did you get stuck? Conceptually, what don't you understand? Where do you get stuck? Did you beat me here? Do you understand what I did now, but you didn't do it yourself? Remember, those are two different levels of understanding. Okay, let's take a look at the back of this page. How much excess reactant remains after the reaction? Okay, when you're calculating excess reactant, excess means leftover, right? So whenever you're trying to figure out how much you have left over, let's say you started with a bag of flour, you use some and you want to know how much you left over, right? Well, we can calculate that. It's whatever you started with minus what you used, and that is what is left over. So that's exactly what we're going to do here. We want to know what we started with, how much we used, and what we're going to have left over. So let's go back to the other side and look at what we started with. So we started with 3.25 grams of NH3. So we can just plug that in. That one's easy. We just have that automatically. 3.25 grams. Remember, our excess reactant is going to be NH3. So we're going to do all of these with NH3. We started with 3.25 grams of NH3. Now, how much did we use? Well, we don't actually have that amount. We need to calculate that amount. Okay, so again, conceptually, how would you figure out how much of the NH3 you actually used? This would be a good time to pause the video and see if you can think that through. So in order to calculate how much NH3 we used, we can do that a couple different ways. We can either go from the amount of water we can actually make to the amount of NH3 it would take to make that amount of water. Or we can go from the amount of O2 that we used to how much NH3 we would need specifically for that amount of O2. Again, this math is all about knowing what your answer means. Okay, I'm going to do the second one because if I made a mistake on the first one, I don't want to use that mistake again on this part. I know how much O2 I started with, 3.50 grams of O2. That was given to me. I didn't have to calculate that. So I'm going to use that amount because I know that I didn't make a mistake on that amount. All right, so we're going to use that amount and we're going to convert to grams of NH3 that we would need to react all of that oxygen. Okay, pause the video, see if you can do that calculation yourself. Grams of O2 goes on the bottom. I'm trying to get out of that. Moles of O2 goes on the top. Moles of O2 goes on the bottom. I want to get out of that. Moles of NH3 goes on the top. Moles of NH3 goes on the bottom. Grams of NH3 goes on the top. Okay, and now I fill it in. So the first is going to be molar mass of O2. That's 32.0 grams of O2 per 1 mole of O2. We have to go back to that balanced equation to get the mole to mole ratio between O2 and NH3. So 5 O2 to 4 NH3. All right, and then we want the molar mass of NH3, which is 17.03 grams per 1 mole. So this was kind of a nice calculation because we already had the molar masses. We figured them out for part A. We can just reuse them for part B. Okay, so let's do this math. 3.5 times 1 times 4 Oops, hold on. Okay, 3.5 times 4 times 17.03 times 1 divided by 32. We also want to divide by 5. We also want to divide by 1. So my answer is going to be 1.49 grams of NH3. Okay, so we have calculated from grams of O2 and we have figured out if I use all of those grams of O2, I'm going to need 1.49 grams of NH3. So we now have, if I go back to what we were originally trying to figure out, now we have how much NH3 we're going to use. So let's plug that in. 1.49 grams of NH3 will get used in order to react with all of my oxygen, and then I subtract those two to figure out what's left. So 3.25 minus 1.49, and I will be left with 1.76 grams of NH3. There is my answer. Okay, let's pause here and see if we can fill out this right-hand column to describe what we did. So this would be a good place to pause the video and see if you can fill that out on your own. Okay, first I started the problem by setting up my little equation to figure out what's left. Start minus used equals what I'm left with. Okay, then I filled in what I know. Which was the start. After that, I had to calculate how much I was going to use. Or instead of putting NH3, you can also put excess reactant to keep it more general for yourself. And we calculated the excess reactant by going from the limiting reactant to the excess reactant. Remember, we also could have gone from our amount of product we made. Oh, actually, which we never calculated water, did we? We calculated NO. You can also go from your product to your excess reactant used. And then I would say we have a fourth step where we subtract our starting, or we subtract what we used from our starting amount to find what's left. Okay, so it's a lot of thinking. I love this problem though. I love it because it's challenging. It takes all these concepts we've been talking about. It takes this math we've been working on for years. How long have you been working on addition and subtraction and multiplying fractions? You've been working on those for years, right? And I love this problem because it actually puts meaning behind the math, right? How many times have you asked, why do I need to know this? When am I ever going to use this? Right? Well, here you go. You're going to use it right now. It's crucial for us to be able to use this. The other reason I love this problem is because it really highlights the difference between dimensional analysis and proportions. If we were going to try to stick with proportions and never learn dimensional analysis, you would have had to set up like 1, 2, 3 times 3, 9 different proportions. You would have had to set up 9 different proportions correctly. A, that's really hard to do. And B, it would have taken you a lot longer to do that than just using dimensional analysis. So we see the usefulness of this skill. Proportions are extremely useful in the right context, right? But there's some contexts where dimensional analysis is really useful too. So embracing that skill is helpful for this problem. And we finally see a purpose in multiplying fractions. It becomes really useful to know how to do that now. And the more comfortable you are with those basic math skills, the more comfortable you're going to be with this concept. So this is a hard concept. It is tricky. Keep working with it. Keep thinking through it. The more you can write down what these numbers mean, the better you're going to be at analyzing these problems. So try it. Try the practice. Let me know what questions you have. I will see you in class.